Hello. In this video lecture, I'm going to talk about the cell membrane. Before we can talk about the cell membrane, though, we need to talk about phospholipid bilayers. So phospholipid bilayers are the primary component that makes up the cell membrane. So they determine the structure, for the most part, of a cell membrane. And of course, structure is function, so it's very important that we understand a phospholipid bilayer structure. Phospholipid bilayers also form many of the organelles that we find inside of a cell. For example, the endoplasmic reticulum and the Golgi apparatus and mitochondria, they all have phospholipid bilayers. The fact that the inside of the cell is separated into separate little units called organelles refers back to a concept called compartmentalization, which just means you have all these separate little compartments inside of the cell. And what separates one compartment from another is a phospholipid bilayer. But today we want to concentrate on cell membranes. We're not going to talk about the organelles. So I want to talk a little bit about a phospholipid first. We've learned about these before. Right? So here we see three different visual representations of a phospholipid. Don't forget, this is a lipid. But it is a unique lipid in that it has both a hydrophobic and hydrophilic component to it. Over here we see the structural formula for a phospholipid. This is the space-filling model for a phospholipid, and this is the cute little icon model of a phospholipid. I'd like to draw your attention first to these long components on the phospholipid. If you remember back to your chemistry lesson, these are long chains of carbons and hydrogens. The grays are carbons and the blues are hydrogens. And carbons and hydrogens in long chains are very, very nonpolar. You have lots of carbon-carbon bonds. Those are nonpolar. Lots of carbon-hydrogen bonds. Those are nonpolar, making these tails here very nonpolar. And of course, nonpolar things are hydrophobic. So this end, this bottom end of the phospholipid, is very hydrophobic. But if we go up further, we encounter something that's hydrophilic, and it's this phosphate group right here. Let's look at the structural formula for that. See if you can recognize what about the phosphate group makes it hydrophilic. This little line right next to this oxygen, that little straight line does not represent a covalent bond, it's too short. This represents a negative charge, right? Water likes things with charge or partial charge, and this phosphate group has a full negative charge on it. So water does like this. The partially positive hydrogens on water are going to love that negative oxygen there. So this upper portion of the phospholipid is called the head, and we say the head of the phospholipid is hydrophilic because of that phosphate group. And this bottom portion, where we have the hydrocarbon chains, also called fatty acids, that part is nonpolar and therefore hydrophobic. We call those tails hydrophobic tails. So when in a watery environment, phospholipids will automatically form bilayers. If you were in a lab and you had some pure phospholipid and put it in some pure water, you would automatically form bilayers. In a bilayer, the hydrophobic fatty acid tails face each other. Right, so you have two layers, that's the bi and bilayer. The tails that are hydrophobic face each other, whereas the heads, the circles, face the watery environment. So there's a question on this slide. It says, where is the water in this picture? I didn't write the word water, I didn't draw water, but water's assumed here. See if you can figure out where exactly is the water. Is it going to be here? Is it going to be here? Is it going to be here? Hopefully you guessed that there isn't going to be very much water at all in here. This is very hydrophobic. Water does not like that. Right? The water will be found here facing the hydrophilic heads and over here facing the hydrophilic heads. Phospholipid bilayers are semi-permeable. Some might call this selectively permeable. And they're a barrier, but they're a semi-permeable barrier. What that means is that some things can cross and some things can't. In order to understand why this is, we need to explore further this hydrophobic, hydrophilic nature of the phospholipid bilayer. If we were to measure the width of a phospholipid bilayer, right, we can say maybe it's 10 nanometers. Right? What portion of that is hydrophobic? So how much of that whole 10 nanometer length or width, whatever you want to call it, is hydrophobic? It's maybe about 70%, like 7 nanometers. So roughly about 70% of a phospholipid bilayer is hydrophobic. So most of the phospholipid bilayer is hydrophobic. To understand hydrophobicity is to understand cell membranes. Right? Cell membranes are made of phospholipid bilayers, and to understand cell membrane structure and function, we have to understand the hydrophobic, hydrophilic nature of the phospholipid bilayer. So let's review hydrophobic and hydrophilic. Right? Hydrophobic, water-fearing. Hydrophilic is water-loving. Right? Don't forget, water forms bonds with hydrophilic atoms or hydrophilic molecules. Right? So down here we see water surrounding a single sodium atom. Right? This sodium atom carries charge, right? And water likes things with charge. Over here we see water molecules surrounding glucose. Glucose doesn't carry any charge. I don't see a plus, I don't see a minus. It does not carry any full charge, I should say. But glucose does carry partial charges, right? Glucose has lots of oxygen-hydrogen bonds, which are polar, and that creates partial charge. So water likes glucose. So water forms bonds with charged things or partially charged things. So polar molecules. Are polar molecules hydrophobic or hydrophilic? Well, if you said hydrophilic, you're correct. Like glucose is polar, and water definitely likes that. Charged atoms, like sodium, are those hydrophobic or hydrophilic? And water likes things with charge, so that also is hydrophilic. All right, here I have a list of items, and I want you to try to figure out if these things are things that are going to mix well with other hydrophobic things. So, what mixes well with hydrophobic things are other hydrophobic things. So, if anything on this list is going to mix with something that's hydrophobic, then it itself has to be hydrophobic. So what we have to do is go through this list and figure out which things are hydrophobic and which things are hydrophilic. Anything that's hydrophilic is likely not going to mix with something that's hydrophobic. So let's look at the magnesium ion. Right? We haven't talked about or read about magnesium ions in this class, but we know it's an ion, which means what? It has charge. And if something has charge, does water like it? Yes, anything with charge is hydrophilic. So a magnesium ion is likely not going to mix with anything that's hydrophobic. Phosphate groups. A phosphate group contains a phosphorus and some oxygens, and one or two of the oxygens can carry charge. So if it's charged, it's hydrophilic, and so it's not going to mix with something that's hydrophobic. Cortisol. Cortisol is actually a hormone that's released by the adrenal glands, and it's important in your stress response, and it helps with inflammation and other things. Cortisol is structurally comprised of a steroid, so it's made of a lipid, right? So cortisol is a lipid that's hydrophobic. So cortisol would mix with hydrophobic things. How about glucose? It doesn't carry full charge. It's not an ion, right? But is it hydrophobic or hydrophilic? Right? C6H12O6. You have a lot of oxygens there. They form oxygen-hydrogen bonds, which are polar, so this will be hydrophilic. Not going to mix with something that's hydrophobic. Hydrogen ions. It's an ion. It has charge. It's hydrophilic. It won't mix with something that's hydrophobic. Water. Well, water does like itself, so water is hydrophilic, right? It's not going to mix with a hydrophobic thing. Amino acids. Amino acids were the subunits to proteins. Amino acids, there were 20 different kinds, but the main components to the amino acid were very polar. You had nitrogen-hydrogen bonds and oxygen-hydrogen bonds there. So for the most part, amino acids are going to be polar and then hence hydrophilic. I will say that there are some amino acids that have a variable group that are hydrophobic. That's something that we don't want to get into. In general, we're going to say that amino acids are hydrophilic. So if they're hydrophilic, they won't mix with something that's hydrophobic. Then we have triglycerides. Triglycerides are a lipid. Since they're a lipid, they are hydrophobic, and they will mix with other hydrophobic things. Okay, so I want to talk about what things can cross a phospholipid bilayer. So we've already established that the majority of the phospholipid bilayer is hydrophobic. Roughly about 70% of the phospholipid bilayer is hydrophobic. So the real question becomes not what can cross the phospholipid bilayer, but what can cross the hydrophobic portion of the phospholipid bilayer. So I have some general rules for crossing phospholipid bilayers unaided. You can cross the phospholipid bilayer if you're hydrophobic, because the phospholipid bilayer is mostly hydrophobic, and hydrophobic things mix well with other hydrophobic things. So if you're hydrophobic, you can cross. Rule number 2, you can cross if you're really small and do not carry full charge. Okay. So small, large, those are relative terms, right? So what do I mean by really small? By really small, I mean 3 atoms big or less, right? So you have to be made of 3 atoms or less, right? And you can't carry full charge. Partial charges could be okay, but you can't carry full charge. So let's look at talk about a couple examples, right? What about this little purple triangle? Let's say this is water. According to the rules, can it cross? Well, it's not hydrophobic, right? But let's look at the second rule. You're really small and do not carry full charge. Water is really small. It's 3 atoms, right? And that's the rule. You have to be 3 atoms or less. Does it carry full charge? No, a water molecule does not carry full charge. It carries partial charge. So water actually can cross a phospholipid bilayer unaided, which almost sounds kind of like an oxymoron, right? Because we've established that this area in here does not like water, and water just crossed. Well, the reason why water can cross is because it's so small, it's practically invisible to the hydrophobicity of the layer. And really, water does have a hard time crossing, to be honest, but it can cross. All right, how about this big purple thing? Let's say this is supposed to be a steroid hormone. Can it cross? It's huge. It's definitely bigger than 3 atoms, way bigger. It can cross because it's a steroid, which means it's hydrophobic, so it is able to cross. How about this? Let's say this is glucose, right? Is glucose hydrophobic? Nope, it's hydrophilic, right? Is it less than 3 atoms big? Let's see, it's made of 6 carbons, 12 hydrogens, and 6 oxygens, so no, it's definitely bigger than 3 atoms. And it's polar, and it does carry partial charge, so it's hydrophilic and it's too big, it's not getting across. So you may not cross if you're large and polar, so if you're 4 atoms or bigger and polar, you can't cross. You also can't cross no matter how big or small you are if you're charged. So even if you're a teeny tiny little hydrogen ion, you're made of nothing but a single proton. It doesn't get any smaller than that. It's the smallest thing we really come into contact with in this class is a hydrogen ion, a proton. It is an ion. It cannot cross the phospholipid bilayer unaided. Okay. So let's say this little plus sign here is representing a sodium ion. It is 1 atom big. That's it. It's definitely falling within the realm of you are really small, right? It's 3 atoms or less. It's just 1 atom big. But it does carry full charge, so it cannot cross. All right, what we're looking at here is the same list that we looked at earlier where I asked you, okay, which of these things can mix with something that's hydrophobic? And the whole point of that activity was to come to this activity and see that, okay, the phospholipid bilayer of the cell membrane is going to be mostly hydrophobic. So if you want to cross the phospholipid bilayer, right, you have to be able to cross that hydrophobic barrier, right? So which of the following things can cross the phospholipid bilayer unaided? So apply our rules here, okay? You can cross no matter your size if you're hydrophobic, right? Now, you can also cross if you're 3 atoms or less and do not carry full charge. Let's see who can cross. A magnesium ion can't cross, has full charge. Phosphate group can't cross, it has full charge. Cortisol is huge, but it can cross because it does not carry charges of any kind. It is hydrophobic. Glucose cannot cross. It's more than 3 atoms. and is polar. A hydrogen ion, very tiny, but it cannot cross because it carries full charge. Water, it's 3 atoms or less, so it's small, and it does not carry full charge, so it can cross. Amino acids, they're polar and they're bigger than 3 atoms, they cannot cross. A triglyceride, it's big, excuse me, but it's hydrophobic, and so it can cross. Now, we've been talking about phospholipid bilayers so far as if they were pure phospholipid bilayers, but in reality, there are going to be other things that are a part of this bilayer, like proteins. And the proteins serve lots of different functions, and we'll explore some of this in just a bit.